All right, hey everybody, how's it going? So we're just going to talk through a few notes today. This is introducing work, energy, and machines, and this has to do with your design challenge that you guys just completed. So definitely pull out a notebook and make sure that you're recording these notes because these are important to know. We'll be using the kind of formulas that we talk about for the rest of the quarter. So let us go ahead and get started with the joke of the day. So why shouldn't you write with a broken pencil? Well, because it's pointless. Get it? There's no point because it's broken. Anyways, so the design challenge that you guys just did was to design a machine that can lift a 20-pound weight 4 feet in the air using only a 5-pound weight. And hopefully you guys had some struggle with this. Hopefully you guys came up with some creative ideas. I'm excited to look over them. But it seems kind of impossible when you really just think about it, because how are we supposed to get a heavier object up higher, right? We're supposed to add energy to it somehow using a less massive object, right? So using a smaller force, we're able to then apply a bigger force to this object to lift it up. How are we able to do that? And the answer is that we can use machines. And so what exactly is a machine, right? Well, a machine is just a tool or combination of tools that can be used to transfer energy. And a tool is just something that we can kind of create or build, just a device. Hard to kind of describe, but you know like what a tool is. But they transfer energy, and so common forms of energy that we'll typically see and talk about in this class are gravitational potential, right? Energy in the height above a surface within a gravitational field. Kinetic energy, that's the energy of motion, either translational motion, so linear motion, or rotational motion, right? There is energy in that as well. Elastic potential energy, that's the energy in the deformation of an object that wants to return to a certain shape, so that's like in springs and rubber bands. And then thermal energy or heat. This is energy that is essentially in the random motion of molecules. It can be important in gases because as gases heat up, they expand and they can apply forces and pressure. But it can also be unideal, like when you're heating up things and getting unnecessary heat due to friction. So one thing of note to remember from physics is that energy is transferred by doing work, right? That is the main way that energy is transferred. And work is applying a force over a distance, right? So by applying a force over a certain distance, you are transferring energy. We can calculate work by taking that force in newtons and multiplying by the distance in meters, right? That is how we can actually calculate the work done, and work is just a transfer of energy. So we're going from one form to another. How do we get from one form to another? We do work. Right. One thing that we'll talk about when we're referring to energy transfers is we'll consider the input and the output, right? So what is the energy coming in? What is the energy coming out? And we can also consider that as the effort and the resistance, right? There's effort work and effort energy being done, and then there's resistance to that work, right? So you'll see effort and resistance and input and output kind of used in the same terms. Input we can consider the force applied over a distance, and output is the force generated over distance. Another important thing to remember is the law of conservation of energy, right? This is why that design challenge seems so kind of hard to do in the first place, is energy cannot be created or destroyed, only transferred from one form to another. So by lifting a 20-pound weight 4 feet, right, we're adding this gravitational potential energy to it, right? Well, how can we get that energy that we add to it using only a 5-pound weight, right? So we can write the law of conservation of energy as the energy in is equal to the energy out. And then within a mechanical system, so within machines, this holds true. It will always hold true. But when we're looking at mechanical systems, we consider the kind of energy that we can put in, which we're going to start talking about kind of human inputs, right? Kind of forces that we can apply. But you could have other energy sources as well. But within this mechanical system, we are concerned about the energy that we're putting in and the type of energy that we're getting out. And usually we have a desirable end type of energy, right? We have something that we want to have done. That energy, we want that energy to be in a final form that is desirable, be it kinetic, be it gravitational potential, be it elastic potential, be it heat, right? But the energy in is equal to the energy out. But then there's also kind of energy that's lost, right? And that lost energy is the energy, that output energy that is in a non-desirable form, right? Which is typically friction or heat loss due to friction. So we could rewrite our conservation of energy equation for mechanical systems as the energy in is equal to the energy out plus the energy lost. And this becomes important when we start talking about efficiency. And the efficiency of a machine, or the efficiency of a mechanical system, is essentially a measure of how much of this energy is lost. Or put another way, how much of our energy that we're putting in is turning into the desirable form that we want, right? And then how much is in an undesirable form, how much is kind of lost, right? In an ideal machine, right, the energy that we put in is equal to the energy we put out. All of that energy that we're putting in is going to the form that we want. But in an actual machine, in reality, we can't really get that. There's always going to be some losses. So you'll see us talking about in this quarter ideal machines and actual machines, right? Ideal mechanical advantage and actual mechanical advantage. And also this idea of efficiency. And we always really kind of want to try and improve efficiency as much as possible, taking our input energy and getting it to the output form that we want with as little lost to those undesirable forms. So that's the law of conservation of energy. And that brings us to simple machines, right? Simple machines are tools that allow us to manipulate how we transfer energy, right? We use these tools to manipulate how we transfer that energy by doing work. And work, once again, is applying a force over distance. So we know due to the law of conservation of energy, the energy we put into a machine is equal to the energy that machine puts out, right? Now we can rewrite that then as the work that we put into a machine, the effort work, is equal to the work that machine does, right? In other words, the resistance work. So if that machine is lifting a load, for example, the resistance work is the energy transferred to that load, right? So our effort work is equal to our resistance work. The work that we apply to a machine is equal to the work that is done by that machine. And so then we can plug in our work formula, right, to say the force effort times the distance effort is equal to the force resistance times the distance resistance, right? In other words, the force that we apply times the distance we apply it is equal to the force that we generate times the distance that we generate it, right? And this is a big equation to remember because this is a key equation that we'll use in analyzing simple machines and how they work, right? We have our effort work over here and we have our resistance or our generated work over here. And they always have to equal each other, right? Minus frictional losses. But in an ideal situation, they equal each other, right? So this is the key idea with how simple machines work. And then by changing our effort force, by using machines in certain ways, right, we can do things that seem impossible, right? We can apply a smaller force over a greater distance, right, to then generate a bigger force over a smaller distance. And that's the big thing. So when we look at the design challenge, right, we're trying to lift a 20-pound weight 4 feet into the air. So we're trying to apply, in order to lift a 20-pound weight, we need to apply 20 pounds to it, 20 pounds of force, and we need to apply that over a distance of 4 feet, right? So our resistance force and distance are 20 pounds and 4 feet. So in order to do that, though, we only have 5 pounds of force that we can apply, right? A 5-pound weight under the force of gravity can apply a force of 5 pounds, okay? So we have a effort force of 5 pounds, a resistance force that we need to apply of 20 pounds, and a resistance distance of 4 feet. So by using this equation, we can calculate, hey, if we apply that 5 pounds of force over a distance of 16 feet, right, then we should, in an ideal situation, be able to lift that 20-pound weight 4 feet into the air, right? And in reality, we'd have to probably move it more than 16 feet because of frictional losses, but we should be able to do this, right? This does not violate the law of conservation of energy. And so the question then becomes okay, well, how can we then apply this 5-pound force over a distance of 6 feet and only have the object be lifted 4 feet, the 20-pound object be lifted 4 feet, right? How can you make that work? And that's where simple machines come in, and that's what your guys' homework is you're going to do a little scavenger hunt, looking over there's 6 basic types of simple machines, any of which could be used for this. One is a lever, another is a wheel and axle, and any of those could be used, right, to kind of solve that design challenge, although there's some that are going to be better than others, right? And so for the homework, I want you guys to look at those different types, and we'll continue to talk throughout this week about how those different types follow this equation, and how can you use this equation with those types of simple machines to design them in specific ways to accomplish specific tasks. So this is going to be due at the end of class, so make sure you get that in at the end of class, and I will see you guys tomorrow.